Hello again, this is Tu and Seth, and in this video we'll be just giving a general introduction to Monte Carlo simulation, kind of what it looks like mathematically and how it can be implemented, and really just the purpose of it. So, from what we know from mathematics, we have integral evaluation, which we can do in general for most functions. But when those functions gets really complex, what we'll be looking into is Monte Carlo. Now, normally, we want to look at what the integral is that we're looking at and how it can be evaluated. For example, if we have a simple function such as f of x equals x squared, say, we can simply take the integral of that, x cubed over 3, and then go on support from wherever our origin is to the end, and that will give us the area under the curve. But in some cases, we'll be looking at complex functions where Monte Carlo is needed, and what that will provide for us is simply an area estimation rather than an exact integral. Now you might be asking yourself, why don't we just do integration? Well, the problem with that is that oftentimes we'd simply can't do that mathematically, or the software won't support some of the complex functions that we have going on, or they'll produce very complex stepwise functions that are very hard to evaluate. And what Monte Carlo will be accomplishing by simulation of the data points and finding the area is really just finding a general idea. We can't exactly pinpoint. We'll be using different methods to find the estimate, as well as the standard deviations, so that we can see how much it varies between our different sample runs. But we're just getting a general idea of what the precise answer would look like for that distribution, and that brings us to the topic of expectation, which is simply the mean of a bunch of data points. So for expectation, what we have is, say for example, we have this ridiculous distribution on the axis, and we're going to be looking at different points, and say here we have x equals 1, and we know that where x equals 1, say f of 1 equals, let's say it equals 2, and we'll gather a bunch of different points randomly like that. And once we do that, we can find a mean or expectation, and that will provide us with a general understanding of what the area under the integral will be within our support that we have set up. Now in Monte Carlo, an important consideration is that we can estimate the value of really any integrand, no matter how complex that integrand is. So we can look at functions that really, when we look at first glance them beside a dx, say, within an integrand, we would say that it's nearly impossible to solve. But with Monte Carlo, we're able to solve those problems simply with conducting sampling of random points and then picking up that expectation that we talked about. And really that expectation is what we have in the combinality of integrations, probability densities, and fissionable materials. We can find that expectation so that we can perform some simulation and provide a rather accurate estimate to what we're looking for precisely. Now essentially what we're doing, as I said before, we're essentially setting up random dots and finding the expectation of those so that we can meet the requirement of, say, a certain variation, and have the confidence to say that within normal parameters we can expect this value. And As I said before, we have the example of fissionable or fusionable materials, where we have very small pockets of energy that are jumping around at different vectors. One example is an atom bomb that will have the energy distributed somewhat randomly, and through these Monte Carlo simulations we can give an expectation of how much damage will be done, different things such as the blast radius, and useful things such as the variation, so that we can provide an estimate of how much damage will be done by that. And this is very important, because if we were to check all the possibilities for this, we would run out of time and all the stars would burn out in the entire universe. So it is a very useful tool in that sense. And we will now look at a MATLAB example where we have two input variables, x1 and x2. Here's our function right here, and we will be estimating to find the maximum in this function. And here we are in MATLAB. We can see that in our function we have it declared, and we have some initial values set up to start at, so that we can slowly climb to what we believe to be the maximum. And we'll continually generate random numbers within a distribution, in this case the normal random distribution. And as we're going through, those new tested values will be checked using a greedy algorithm, just to see whether or not one is better than the other, and then that x value will be, those two x values rather, will be held onto, and the z max value, which is the resultant value of the function, will be held onto. So if we go ahead and run this, we can see that our z max turned out to be 4.6 times 10 raised to the third. We have values for x1 of 31.5 and x2, and we can see here that we began at 3.3, and that value is rather low, but as we're climbing up we can see that our z value is increasing as we're moving in the x and y within that distribution that we established, and eventually as we're closing to the result that we want, we can see that the points are getting closer and closer to the maximum. And that's just a little look into Monte Carlo, and we appreciate your viewing, and we'll see you soon in a future video.